Okay, we're live. Welcome to Math with Doug. Welcome to Geometry with Doug. We are still in a geometry unit, but I decided to call this lesson Pythagoras because I didn't want to write Pythagorean Theorem. It's long. And what else is there to talk about as we introduce the lesson besides this beautiful drawing, which I'm going to talk about soon? I'm not wearing a sports jersey for a change. That's different. And the dog is not here. And the weather outside is boring and I don't want to talk about it. So let's just get right back into the math. We've drawn a lot of triangles lately. And right triangles are among them, but we've learned to draw all sorts of different types of triangles. So I drew a right triangle and I decided to make it have side lengths of 3, 4, and 5 units. What is the unit? If I were doing it on paper, I might have chosen 3 inches, 4 inches, and 5 units, 5 inches, but that would not make very much sense on a chalkboard. If I tried to draw it actual size, it would be too small. So I decided to use decimeters. So a decimeter is 10 centimeters. Therefore, 3 decimeters is 30 centimeters, and that makes for a good, useful size for us to be able to see what we have. So we have 3 decimeters, 4 decimeters, and 5 decimeters. It's not a scaled drawing. It's drawn that size. But why did I draw squares sticking away from all 3 sides? Well, first of all, just to point out that you can always do that with a triangle. You could draw any triangle, and from each of the 3 sides, you could draw squares. That's kind of neat, but I wanted to do it with this triangle for a reason. Because what we learn when we understand Pythagorean Theorem, which I'm not necessarily going to try to prove in this lesson, what we learn is with the right triangle, there's this relationship that has to do with the area of these squares, which is just like another geometry lesson. It's kind of neat, it's kind of weird, but let's look at it. If this line is 5 decimeters in length, and if this is a square, then we can find the area of this square very quickly using the area of a square formula, which is area equals s squared, sine length squared. In this case, that means 5 squared, and that is 25. And it is square units, so I'll write decimeters squared. Trying to remember, make sure that I don't use the wrong unit, so I'm going to quickly Google something. Yes, decimeter is dm. I always get a little nervous with decimeter and decameter. Am I using the dm? Is that the decimeter? So it is. Okay, so good. We have the area of this square. It's 25 square decimeters. And then we can do the same thing with this one. Why am I doing this? Well, I will explain. So the area of this square is going to be 4 squared, which is going to be 16 decimeters squared. And then the area of this little one here is going to be 3 squared, which is going to be 9 decimeters squared. But what's interesting is 16 plus 9 happens to be equal to 25. Would that happen with any triangle I could draw? No, but it would happen with any right triangle I could draw. And that's kind of neat. In a way, it could help us remember the formula. What's the formula? Oh, well, I may as well put the formula together right now. So let's say we decided to call the hypotenuse C. And yes, you often see it with H, but I choose to use C. I have my reasons. And then I didn't really leave room here, but let's say we call this side A, and we'll call this one side B. Okay, so now what we can do is we can say, we have this relationship where we know 9 plus 16 equals 25. We know that. But 9, how did we get 9? Oh yeah, it was 3 squared, so we can rewrite it as 3 squared. And then the 16 was 4 squared. And the 25 is 5 squared. Okay. And then what we can do if we want to go one step further is we can replace the 3, the 4, and the 5 with these letters. So the letters are A and B and C. So we end up with A squared plus B squared equals C squared. And we have the formula, Pythagorean Theorem formula. So that's neat because this formula works for all right triangles. If you tried to do this little experiment with a triangle that was not right, it would not work. But would it work if we did it with another triangle that was also right? Well, we're about to find out because I'm about to do it. Let me keep an eye on the time. Oh, we're very early in the lesson. That's pretty good. We're covering ground nicely. Now I have to erase this beautiful diagram that it took me so long to draw. But I'm going to leave this up here for now. So let's get into the erasing. Okay. I want to draw another right triangle, and I am again going to try to draw it neatly. I'll use a protractor to make sure it really is a right triangle. But I'm not going to draw the squares this time. So let's choose another one. Now that 3, 4, 5 triangle is really special. As teachers, we really like having that right triangle, especially when we're introducing Pythagorean Theorem to students. But there are other ones that are nice, that give you nice clean numbers the way this one did. That's why we like it. Because 3 squared is exactly 9, 4 squared is 16, 9 plus 16 is 25. We can see what's happening with the numbers without being distracted by all sorts of decimals. Let me take another one. Should I draw it full size with decimeters? Let me think here. That would be 6 decimeters. This whole thing, which is 2 feet, is just slightly over 6 decimeters. Do I want to try? No. So what I'm going to do is I'm just going to draw a right triangle. And this time it's going to be a scale diagram. I'm not going to bother saying what the scale is. But I'm going to label it with the side lengths that I want to use. So let me get a right angle first. And then I'll get my ruler back and I'll make it bigger. Let me think here. Let's call this, yeah, this will do. I'm actually drawing this pretty much the same size as the other one that I drew before, but this time it's not life size. It's smaller than life size. So let's go all the way to 40 here, and then I connect these two, and we have a right triangle. And I'm going to use the ABC again. So I'll say here, A equals, and I'm going to make this shortest side of the right triangle 6 units. 6, whatever the units are, 6 units. And then this medium length side is going to be my B, and it's going to be 8 units. And C, which is my hypotenuse, is going to be 10 units. Okay. Now let's play around with this. What did we do before? I didn't draw the squares, but we can still imagine the squares are there. So we could say, well, if this is going to work with right triangles, then I can write the formula, a squared plus b squared equals c squared. And let's see if it works with this triangle. A is 6, so I have 6 squared. And b is 8, so I have 8 squared. And c is 10, I have 10 squared. 6 squared is 36, 8 squared is 64, and 10 squared is 100. And it's working. I knew it would work, because it works with all right triangles. But I was carefully selecting right triangles where we can avoid all sorts of crazy decimals. So 36 plus 64 equals 100. We have just verified that this formula works with this right triangle too. Now let's talk about all of the really nice clean number right triangles that I could make if I wanted to give students lots of different triangles to practice with, but I was trying to avoid having all sorts of decimals because I want the students to practice this and feel good about it. And what did we do here? We had 3, 4, and 5, but this one is 6, 8, and 10. I'm doing a simple little trick here, aren't I? 6 is twice as long as 3, 8 is twice as long as 4, and 10 is twice as long as 5. So when I'm trying to come up with right triangles that I can use to create examples of this where we will avoid all sorts of decimals. Well, I'm seeing a pattern here. We have 3, 4, and 5. They work together. And we can see that. And then if we double each of them, we have 6, 8, and 10. That works. So therefore, I could come up with more if I keep on multiplying the 3, 4, and 5 by different whole numbers. So what if I multiply instead of by 2 to get 6, 8, 10? I multiply 3, 4, and 5 by 3. I'll have 9, 12, and 15. Okay, so let's see if that one verifies as well. What I'll do is I'll remove these numbers from this diagram, and then we will make the shortest side 9, the medium length side will be 12, need more chalk, and the longest side will be 15. And then we can try the formula again. A squared plus b squared equals c squared. I'm making sure everything shows on the video. A squared plus b squared equals c squared. Let's plug in. 9 squared plus 12 squared must be equal to 15 squared. Now the numbers do get bigger, and maybe you will end up having to use a calculator eventually when you get to the larger numbers, that they're not falling within the 12 times 12 multiplication tables anymore. But even with the calculator, that's still kind of easy numbers to deal with. 9 squared is 81, 12 squared is 144. If you don't know that what 15 squared is yet, well, you will, because it's going to happen a lot in math. 15 squared is 225. Is 81 plus 144 equal to 225? 4 plus 1 is 5. Let's do it like this. 4 plus 1 is 5. 4 plus 8 is 12. Carry the 1, and then the 1 plus the 1, oh yes, not sorry, the 1 plus the 1 that was carried is 2. Yes, it worked. Okay, and of course use the calculator, or you just already know that 15 times 15 is 225, which is something I already knew. Seen it a lot. Okay, so this keeps working. So that means I can come up with as many examples as I want that have nice clean numbers without all sorts of decimals for students to practice with while they're new to using Pythagorean Theorem, simply by taking the 3, 4, 5 and multiplying them by different whole numbers. 3, 4, 5 times 4 would be, I have it written over there, 3, 4, 5 times 4 would give me 12, 16, and 20. That's going to work. 3, 4, 5 multiplied by 5 is giving me 15, 20, and 25. I can just keep doing this forever. Let's go really far and do a crazy one. We could have 300, 400, and 500. Now, am I obsessing too much over these really clean rectangles where I get to do the math without showing decimals? Well, maybe so, because the thing is, Pythagorean Theorem does not only work when you have sides that are exactly beautiful whole numbers in their lengths. Pythagorean Theorem still works, and it works for any right triangle. But I'm still going to do the 300, 400, 500 example, because that's kind of fun. Let's see here, I'm going to erase a bunch of stuff. I'll erase this, because I think we understand the pattern now. I'll leave that one up there, I'm proud of it. Okay, so what if we had 300 squared plus 400 squared? Would it be equal to 500 squared? Didn't really leave very much room there. So I'll put a wiggly line now. Even I'm reaching for my calculator at this point on, and I might be able to do this in my head, but I don't want to be show-offy and then make a mistake because of it. So 300 squared, 300 times 300 equals 90,000. Woo! So big that I have to move further down to make room for it. 90,000. 400 squared. 400. This time I'm not doing 400 times 400. I'm doing 400 and then using my x squared key. 160,000. I guess I should put little commas. Nope, put that one in the wrong place. There. And does that equal to 500 squared? 500 squared. 250,000. Messy. 250,000. Is 90,000 plus 160,000 equal to 250,000? Yes. 90,000 plus 160,000 equals, yes. So it keeps working. And we've come up with a way to come up with a lot of triangle examples where the numbers aren't always just 3, 4, and 5 every time, where we're able to see that this relationship works without being distracted by crazy decimals. Why do I call them crazy decimals? Decimals are fine. There's nothing wrong with decimals. We like decimals. We're good at working with decimals, so we don't mind when they creep into our triangle problems. Let's look for one more though. When I continue that 3, 4, 5 sequence, if I go far enough, I eventually get to, say, 24, 32, 40. No, I don't want that one. 21, 28, 35. Okay. And how did I get that? I multiply 3 by 7, 4 by 7, 5 by 7. So you can see that the pattern. Therefore, I can make a triangle with these 3 sides, and it would work. But am I making it too obvious? The students all very good with the multiples of 3, multiples of 4, multiples of 5. How could I try and trick students into thinking that I didn't do this and follow this pattern? What if I use 210, 280, and 350? Okay, that's multiplying each of these by 70. Is it going to work? Yes, it's going to work. 210 squared plus 280 squared is going to be equal to 350 squared. Okay, Doug has some erasing to do. I'm going to erase this finally. I'm going to erase all this other stuff, but not the thing I just wrote down. And I'm just going to finish this example, and then we're going to start doing some other stuff with this formula. Okay, 210 squared, 210 times 210, 44,100. I guess I should put it here. 44,100 plus 280 squared, 280 x squared equals 78,400. It doesn't look quite so clean, but I still don't have decimals here. 350 squared, 122,500. Is it true? 44,100 plus 78,400 equals, yes, 122,500. Okay, that's cool. Let's see now. Is this how we use the formula? Not really. This is introducing the formula. When we use the formula, we usually know 2 of the sides, but we have to find the third side. That's where you use a formula, when you have an unknown that you're trying to find. So let's do that. I'm going to change my problem, but this time I'm going to choose from my list of easy ones where I'm still avoiding decimals, 27 and 36. So this is 27 and this is 36. And I realize that you know the pattern, so you'll be able to figure out what this is. But I'm going to pretend I don't know what this is, and I'm using Pythagorean Theorem for the formula to solve it. So a squared plus b squared equals c squared. And then I fill in the numbers I know. A is 27, b is 36. 27 squared, 36 squared equals c squared. Okay, now this is starting to feel more like a math problem. What is 27 squared? 729. And 36 squared? 1,296. But when I add those two together, plus 729 equals 2,025 equals c squared. So therefore c has to be equal to the square root of 2,025. I can write that like this. Therefore c is equal to let's square root that. At this calculator, press buttons a few times, but I can do that. 45. Now over there in my list of beautiful sets of numbers that are all multiples of 3, 4, and 5, where I had 27 and 36, the other number was 45. So I knew that would happen. Okay, and then units. I didn't really bother with units of measure through all of these examples. One of the things I like to tell students is a good idea to do when you get to these math problems where they didn't give you a unit. I like to use the word units as my unit. So what I would say is C equals 45 units in length. And that's helpful to be able to do that because it's not wrong. The teacher who's correcting your question isn't going to say, I didn't say it was units. The teacher knows that unit is a generic term for all the units like inches and centimeters and all the others. What's useful is when you have an area, which sometimes can be the answer to a geometry question, you're able to put the little 2 to show that you know that area units are squared. I like that. So I started doing that when I was a student a very long time ago, and I got the impression that teachers liked it, and I did it ever since. And it stopped me from forgetting to point out that I had square units the occasional time, or cubed units with volume problems. Interesting. All right, so enough with all these clean examples. Have I done everything? No, I haven't. I'm going to take another clean example from my list of multiples of 3, 4, and 5, and do another one, because we don't always use this formula to find the hypotenuse. What if we know the hypotenuse on one of the other sides and we want to find the remaining side? Can we still use this formula? Yes. So I'm sort of giving you a hint at the ending there. Yes, we can. So what will I do? I'm going to erase the 36 and the 27 and this question mark. I'm going to keep the formula up there because we keep needing it, and erase that whole example. Now, which one do I feel like using? I'm going to say C is equal to 30, and one of A or B is 20. I'll say B is 24. So A is the one I'm looking for this time. Okay. If this right triangle is really possible, it's not an impossible triangle. We know what impossible triangles are when you try to draw a triangle that won't work because it disobeys the rules of triangles. If this is a possible triangle, we should be able to find A. C doesn't always have to be the unknown. The hypotenuse doesn't always have to be the unknown. So I am going to keep A as A because I am trying to find it. And then the B squared is going to be 24 squared. And the C squared is going to be 30 squared. Okay, 30 squared I know is 900, but I'll do it in the calculator anyway. I simplify that, we have 900 there. 24 squared, I know I could find it in my head if I really wanted to, but I'm just going to use the calculator. That's 576. And the A squared, we still don't know. So that's what we're looking for. So now we have to do a little bit of algebra because this time our unknown wasn't all alone on one side of the equals like it was in the previous example. So we're going to take the 576 and it is going to be subtracted from the other side. Yes, I am showing the algebra step very quickly, but I know that the students here have learned algebra and know how to do this. 900 minus 576. 324. Therefore, A squared is equal to 324. And that means A is going to be equal to the square root of 324. What I'm doing is I'm square rooting both sides. Why? Why didn't I stop? When I got A squared equals 324, should I stop? I have seen students who would stop when they got there. But no, you shouldn't stop because we're not trying to find out what A squared is. We're trying to find out what A is. So we're not finished until A is isolated. Here it's not isolated, it has another A with it. They're being multiplied by each other. But I can square root A squared and that will give me A. And I can square root 324. And that will tell me how long A is. So square root of 324, 18. A is equal to 18. So I think I'm finally finished using all those clean examples where I avoid decimals because it's time for us to move on to do one of these problems where we could be looking for the hypotenuse or we could be looking for one of the other sides But where we're not trying to avoid decimals because there's no reason to avoid decimals, Pythagorean theorem is still going to work. The only thing that matters is it has to be a right triangle. If you try to do it with a triangle that's not right, then you will start getting answers that don't work out. Okay, so I can keep on, oh boy, I'm really getting a lot of mileage out of this triangle I drew. I'm going to erase everything except the formula. Now, let's see here. What if, I'm going to have to change the diagram. What I'm going to do is I'm going to make this a little longer, this side B. So that was 40 centimeters long, so I'm just going to make it longer so that it's more like, say, 50. There, that's 50 centimeters long. But that's not a right triangle anymore, so I have to do some erasing and fix it up. Okay, now this was 30, so I'm going to just keep it as 30. So far I don't have any decimals, but I'm not getting that magic type of triangle that's a multiple of the 3, 4, 5 anymore, because this is 30, that's 50. Okay, what's going to happen? Well, we're going to find out how long this hypotenuse is, but I'm not going to measure it. I'm just going to draw it using the straight edge, and we'll find out how long it is by using the formula. Why not? There. Okay, so we have a Pythagorean theorem problem. We have a right triangle. We know two of the sides. We're looking for the other. This time we happen to be looking for the hypotenuse. So let's use the formula to find out. A squared is going to be 30 squared, and B squared is 50 squared. Now I am expecting a decimal in my answer, but I don't know absolutely for sure. Maybe by some fluke I'll get something that's not a decimal, and I'll have to keep trying. But let's see where this goes. 30 squared is 900, and 50 squared is 2500. And 900 plus 2500 is 3400. Therefore, C, the hypotenuse, is going to be equal to the square root of 3400. And that is going to be square root 3400 equals, oh yeah, I got a decimal, 58.30951895. I'm going to go to the nearest hundredth. So I'll say C is equal to 58.31. And since there are no units mentioned in here, I will say units as my unit. Now if I don't write the word units, it's still correct because no unit was given in the question. But I like being able to write the word units because that will stop me from forgetting. I get in the habit of always writing down something at the end of my answer, whether I was given a unit in the question or not. And then in the questions where I was given a unit, I won't forget. There's another reason to do it. And we got a decimal. No big deal. What else can happen? Where are we now? Thinking about how much time I have and how many more examples I want to do. So this one gave us a decimal and it didn't stop us. Pythagorean theorem still worked. Oh, I guess I can measure this now. Remember, we had measured that as 30 centimeters and this was 50 centimeters. Is this really going to turn out to be 58.31 centimeters? Well, if we get nice and close, that will be good enough. Let's measure. Oh yes, it's right around the 58, so really close, that's good. Not a bad drawing. Okay, what else can I do? Now this time I got decimal in my answer, but I still gave you side lengths that were nice clean whole numbers. How about if I'll give one nice clean whole number for one of the sides in the problem, but the other one I'll give you a decimal. And I can do that by measuring. So what should I use? I'm going to use decimeters again. Because the size of these triangles is quite convenient. Okay, let's erase everything except the formula here. And I'll erase a bunch of this. And I'll start over, but I'll keep that right angle because it's handy. And I need chalk. Okay. Now in decimeters, I'm going to make this, I'll make it quite long. Some right triangles are quite long and skinny, but they just have to have that right angle. That has to be there. So how about if I put, going a little further, that's, there. That's actually 6.5 decimeters. And in fact, I'll write in a unit this time. So it's decimeters again. We're back with these decimeters because that line is a useful length to me. That's 6.5 decimeters. This one was 3 decimeters, 30 centimeters, but I've erased part of it. So what I'm going to do is I'm just going to measure it, and I'm going to say that is 2.4 decimeters. Okay, so it's again the hypotenuse we're looking for, and this is not long enough. So, how did I know it was not long enough? Because it was just barely long enough. It wasn't even long enough to do this side. And the hypotenuse has to be longer. Because I understand triangles, that's how I knew. Okay, I'm going to connect the ends of these lines to finish my triangle. I'm not trying to measure it. I'm just using a straight edge. Okay, we have a new problem. We're looking for the hypotenuse again. I have to do more problems where it's not always the hypotenuse we're looking for. 2.4 and 6.5. Here's another thing about the A and the B. Do I have to make the A the shortest side? No. The A and the B are interchangeable. But the C has to be the hypotenuse. So I'm going to prove that, I guess. I'm going to illustrate that, not really a proof. I'm going to illustrate that by saying I'm going to call this A. And I'm going to call this B. But this is still C, my hypotenuse is still C. So if A is 6.5, I'm putting the 6.5 squared here, and then the B is 2.4. I could try to do this more neatly, especially now that I have decimals, by using brackets. Okay, so what is 6.5 squared? The math show-off in me says, of course it's going to be 42.25. 6.5 times 6.5 is 42.25. That's just one of those little multiplication tricks. And then 2.4 squared, 2.4 squared, 5.76. Hey, we had 24 squared in an earlier example, and the answer was 576. Now we have 2.4 squared, and the answer is 5.76. Okay. Are we surprised? Doubt it. Okay, equals c squared. This is working. There's decimals all over the place. And I didn't even have to round so far. But 42.25 plus 5.76 is going to be 48.01. Is that going to be it? Okay, teacher who's learned his lesson. 42.25 plus 5.76. Yes, it's 48.01. So therefore, C is going to be equal to the square root of 48.01. And I believe I'm going to have to do some rounding with this answer. Is that fitting? Yes. Okay, the square root of 48.01. 6.92892, so it's a decimal that goes on and on, but I'm just going to call it 6.93. And since I did draw this with actual 2.4 decimeter and 6.5 decimeter sides, that means this hypotenuse, if I were to measure it, should give me 6.93 decimeters, or 69.3 centimeters, for which I need the longer one. But it does have centimeters on here on one side. 69, oh nice. Well, it looked like 69, but 6.93 decimeters is very close to 69 centimeters. That works, it works. But really, this is the whole point. We don't let the decimals scare us. We don't let big numbers scare us. So long as it's a right triangle, this is going to work. We have to be able to use the x squared key in our calculator. we have to be able to do the square root key in our calculator, and sometimes that will be new. When students are learning this, often they haven't encountered the square root key very much yet, but it's one of those things that once you get to it, you will start using it a lot. What should I do next? I think I need to do another one with decimals where it's not the hypotenuse that we're looking for. Looking at the time. Okay. Erasing everything except the formula. This formula is very powerful. We will use it all the time from now on in math once we've learned it. And it is used as the basis for other formulas. It just comes in handy again and again. But of course, only for right triangles. Okay, let me draw one. And I'll draw it at random. And I'll do centimeters this time, so we'll have some larger numbers. So I'll tilt it the other way. I'm going to, there, without looking at how long it was, I drew a hypotenuse. And then I'm going to, kind of estimating this side, but now I'll get my protractor and make sure that it really works. So what I'll do is I'll draw this line down and then get my protractor and use that line to help me draw a proper right triangle. Yes, that's nice. And again, I haven't checked to see how long any of these lines are. But that's going to be a right triangle. Erase that little bit. Now I can measure. But I want to measure the hypotenuse on one of the other sides. I don't want to be looking for the hypotenuse this time. I want to already know it and look for one of the other sides. I think I'm going to look for side B. Well, I shouldn't even call it that. This side, which could be A or B. So let's say I'll label them and I'll call this side A. Side B is what I'm looking for. And side C is my hypotenuse. Now, in centimeters, .56. In centimeters, oh good, this is giving me a 0.5, 24.5, is that a 24? No, 29.5. Okay, so I can find out what B is. I have a decimal in one of the sides I'm given. I'm not going to be surprised if there's decimals in the answer. Let's do the formula. I'll do it over here. A squared plus B squared equals C squared. And the A is 29.5. And the C is 56. I'll move my calculations over to the left a little bit. And let's get the calculator and get busy. 56 squared. 3,136. 29.5 squared. 870.25. And here come those algebra skills. If I move this to the other side, B squared equals 3,136 minus 870.25. Subtract in the calculator. And I get 2265.75. But that's still B squared. We don't have our B yet. B is going to be equal to the square root of that. Oh, I'm not showing B equals square root of the number. I'm skipping that step, but don't skip too many steps. Square root of 2,265.75. $47.59989, and if I want to keep rounding to the nearest hundredth, which is what I've been doing so far, that means it's going to be 47.60 units. Okay, and and I did measure this. You don't have to measure, right? I can draw a triangle and just sort of choose these numbers. And the formula still works, but I'm choosing to measure because I want people to feel confidence in it. So with these 56 centimeter, 29.5 centimeter sides in a triangle where I used a protractor to try to make sure it really was a right triangle, I should get an answer when I measure this B. It should be quite close to this, with any difference just being measurement error, drawing error, or rounding error. And I don't want to call it rounding error, just rounding. Rounding changes the numbers a little bit. So 47.6 units, how close will we be? It's definitely less than 48 centimeters when I measure it. So it's 47 point something, it's more than 47.5, so that's pretty good. I like this formula. What if there were a fraction? Would that bother us? I want to move on to the trapezoids, and I'm looking at the time. But I think I want to do one more example, and I'm throwing a fraction in there. Why not? What if you were using this and you got used to the decimals, and whole numbers are no problem, the decimals are no problem, it's always working, and then suddenly, oh no, there's a fraction. Well, I may as well put a fraction in there, or two, and we'll see. And how will I choose to do that? I know, by using fractions of a meter. But I'm not trying to draw it life size. I'm going to draw a line, and then I'm going to use that line on my protractor to draw a perpendicular line. And now I'll go back to the ruler, and I don't have to make this much longer. In fact, I'm just going to make it just a little bit longer, and I'm going to let this be my right triangle. It's a right triangle. It's kind of a tall, skinny one this time. There's my right angle. And let's say fractions of a meter. Let's see if I can come up with something that's kind of cool, but I'm kind of estimating this. So there. 0.25 meters. And then, so it's, 0.25. I said fractions and then I wrote a decimal. So we know that 0.25 is equal to a quarter in fractions. So 1/4 meters. Are fractions going to bother me? Of course, students know that they can turn 1/4 into 0.25 if they want. So they'll get the right answer. Fractions of meter. This is about 2/5 of a meter. Okay. Oh, and I'm looking for the hypotenuse again, but that's fine. We've had enough examples where we're not looking for the hypotenuse. 1/4 and 2/5 are my A and my B, and it doesn't matter which is A and which is B. I'm going to call this A this time, call this B. Say, what is the length of our hypotenuse? A squared is 2/5 squared. B squared is 1/4 squared. Are the fractions causing any problems? Not so far. 2/5 squared is going to be 4/25. How did he know that? I just happen to know that 2 squared is 4 and 5 squared is 25. The fraction squared, well, it would be, we know that. We know how to multiply fractions. 2/5 times 2/5. That's what 2/5 squared means, right? 2 times 2 is 4, 5 times 5 is 25. I didn't really even have to show that, did I? Okay, 1/4 squared is going to be 1/16. But at this point, it's getting awkward. Am I starting to want to turn it into decimals so that I can finish it sooner? 40/25, 1/16, trying to find the common denominator of that. I think I'm going to switch it into decimals. And of course, this is one of the reasons that we learn decimals. And one of the reasons why we don't always do everything in fractions. Sometimes the fractions are more convenient. Like squaring that may have been easier in fraction form than if it had been in decimal form. Sometimes decimals are more convenient. So 4/25 is going to be 0.16. And 1/16, oh, I should know that. That is such a carpentry measurement. 0.0625? Is it? 1 divided by 16. Yes, 0.0625. Okay, so the fractions thing, I guess that experiment's kind of over because we're going to get our final answer, but I'm in decimal form. 0.0625 plus 0.16. 0.2225. Ooh, 0.2225. And therefore C is equal to the square root of that. Decimal. Getting it in a fraction would have been a bit of a pain, I have a feeling. I'm getting 0.47 rounded to the nearest hundredth. 0.47 meters. And that's kind of logical. That's slightly less than half of a meter. I believe, looking at this line, that it could be slightly less than half of a meter. Of course, it's working with the diagram because of the fact that I was measuring these with the ruler and not just throwing down numbers and guessing. Okay, so 0.47 of a meter is our answer, and therefore I should be giving a unit, and there it is, meters. 0.47 meters. Now, if I really want that in fractions, that's equal to 47 hundredths meters, which is not reducible. But do I really want to do this? Because that was rounded. So we know that if we were to finish it in fraction form, we would get a fraction that's very close to being equivalent to 47 hundredths. But our fraction answer would be more exact than this because we did a bit of rounding in between. Okay, now not very much time left. I have time to do at least a couple of trapezoids, and that's what I want to do. So I'm going to start by drawing an isosceles trapezoid. Now, why am I doing this? Because I want to use Pythagorean Theorem, which I erased. I want to use Pythagorean Theorem in another geometry situation. And the trapezoid is an opportunity to do that. So I'm going to start by drawing an isosceles trapezoid. What I'll do is, I don't really want to measure it. So I'm not using oh, what a mess. I'm not really using the entire length of this meter stick. And I think I have a bit of erasing to do for this drawing. I'll try and tidy this up a little bit. Yeah, it's not too bad now. Okay, but what I'm going to do though, because I want this to be isosceles, is I'm going to measure a certain number of centimeters from each end and make a mark. There. No, I want to go further. I'm going further. I'm going to go to here instead. So I'll move that mark. And there. Remove that mark. Okay. Now, how high do I want to go? We don't know how high this is going to be, and if we were using the area formula, we would need that. But we're finding the perimeter of this trapezoid. That's what we're doing. So I'm trying to keep my straight edge parallel to this one, because a trapezoid has to have two opposite sides that are parallel to each other, or else it won't be a trapezoid. Yes. And I'm staying right above that mark I made, and I'm drawing a line, and I'm trying to end it right above that mark I made. So it may not be a perfect drawing, but I believe what I just did was to create an isosceles trapezoid. Okay, now, how far apart are these two little marks I made? I'm actually going to give the real measures in centimeters, and I would say that is 40 centimeters. And that means this is also 40 centimeters. So we have some information about this thing too that'll help us to find the perimeter. But what I'm not giving is this side's length, which has to be equal to this side's length because it's an isosceles trapezoid, so these two sides are equal in length. And how long was this? That is 25 centimeters. And so is this one over here. So we have a lot of information that helps us find the perimeter, but we don't have all of it. We know the perimeter is going to be 40 plus 25 plus 40 plus 25 plus this plus this. And we know these are equal to each other. What can we do? What we can do, well, I have this one in my hands already, may as well keep using it, is we can complete this right triangle. And I guess I'll complete this one at the same time. Look, I'm able to draw these two little right triangles inside my trapezoid, and that's helpful. Do I have enough information? It didn't give enough information, so I need the height. Not giving this, doing it on purpose. I want us to use Pythagoras. Okay, that is about 27 centimeters. And this will be the same. Okay, now we have enough information. What we can do is we can work just with one of these right triangles, and we could use either one because we have enough information about each of them. This one, I didn't label it, but I can, because it represents the height of the trapezoid, and the whole trapezoid has to have that height between these two parallel lines, parallel sides. So I have my choice of two different right triangles. Well, two different, I shouldn't say different. I have my choice of two right triangles that are both going to have the same measurements because of the fact that it was isosceles this time. We can do this sort of thing when it's not isosceles as well. Okay. What will I do? What I'll do is I'll just visualize, and I often like it when students draw the triangle they're working with separately from the big diagram so they can see what they have. And if this is 27 and this is 25, then I can use Pythagoras' theorem to find the length of the hypotenuse, and then I'll have enough information to find my perimeter. Do I have enough room over here? Yes, I do. I'll start here. A squared plus b squared equals c squared. That's a c. And I'm going to call A and B, the 27 and the 25. Again, they're interchangeable so long as the C is your hypotenuse. So 27 squared plus 25 squared will be equal to C squared. This is going to be 625. I know that from memory. But the 27 squared, I'll get with the calculator. 27 squared. 729. Just enough room to write that. How small is this looking on the video? It's kind of small. 729 plus 625, 1,354. He says, starting to write a little bit larger. Therefore, the C, the length of the hypotenuse, the length of this side of the trapezoid that I need, is going to be equal to the square root of 1,354. Which is 36.7967. I'm going to call it 36.8. Units. Oh no, it's not units. I don't want to use the word units because the unit was given in the problem, remember? So it's centimeters. Therefore, the perimeter of our trapezoid is going to be equal to 40 plus 25 plus 40 plus 25 plus 36.8 plus another 36.8. I didn't leave room for the equals. That's a lot of numbers. Okay, so the perimeter is equal to the total of all of those put together. Now this is working with me only having to do the formula once because it was isosceles, so these two right triangles are identical. Therefore, if this is 36.8 centimeters, that has to also be 36.8 centimeters. We can see that this side, the other two sides are 25 and 27 in both cases. That makes sense. Okay, let's add them together. 40 plus 25 plus 40 plus 25 plus 36.8 plus 36.8 equals 203.6 centimeters is the perimeter that I got, partially by knowing some side lengths of the original trapezoid, and partially by knowing how to use Pythagoras' theorem. Interesting. That was fun. And there is time to do one more, and I'm going to do one more. But I don't want to use an isosceles trapezoid this time. Now, I could use a right trapezoid, or just an irregular trapezoid. I have a choice. I don't really know what I want to choose. I'm going to do the right trapezoid one. and I'm going to see if I can do it quickly. So I'm erasing everything. At least we know a right trapezoid will be fairly easy to draw because there's a right angle in it. We have a protractor. So let me draw this. I'll move over here a bit and I'll draw this. And a right trapezoid has two right angles in it. Two. Not just one, two. So drawing one right angle, like this. There's that right angle. But what I'm going to do now is I'm going to swivel this around, get the 90 on this line, and start drawing another side, which creates another right angle. And then I can do all sorts of things with how long I want to make this, but I don't want to make it a rectangle because that would be too easy. Let's find the perimeter of this trapezoid, which is a right trapezoid. Interesting. Now, I have to have some information. So this time I'm going to make up values, but I'm going to try to make sure the values are reasonable. If this were to be 10 units, I'm not saying what type of unit it is, and if that were 10, this is believable that it would be 8. And then if that's 8, I could call this 25. So it may not be perfect, but the calculation will be perfect. The drawing may not be perfect because I'm just sort of using reasonable logic to figure out side lengths that sort of make sense with each other. But we don't know how long that side is, so we can't find the perimeter. What is the perimeter of this trapezoid? What we can do is we can do what's called dropping an altitude or dropping a height, drawing a height here. If I want, I can put it as a dotted line. I kind of like doing that. This is also going to be 10 because these two sides are parallel to each other. So now we have, I put myself in a position of having to find the hypotenuse again. I didn't really necessarily want to, but I'm just going to go ahead and finish this. With this right triangle, and I can put that little symbol there if I want, I can say a squared plus b squared equals c squared. More chalk, please. And the 10 and the 25 are my a and my b, but it doesn't matter which is which. That's 100. 25 squared is 625. Therefore, c squared is equal to 725, and c is going to be equal to the square root. I choose to show it this time, of 725, which is going to be, that's supposed to be an equal sign. Square root of 725, how much time do I have left? Square root of 725. 26.925, so I'll call it 26.93. 26.93, and it didn't say what the units were, so I'm just calling it units. I want to do it again. I like it. It's good. We're finished. I want to do it again though. This time, I'm changing the numbers, keeping the same diagram to save time. This time, we're not going to know the height. That's not going to be 8 anymore. I'm going to say that is 5. But if that's 5, this shouldn't be 25. I have to change it. I'm going to say it's about 17. Ooh, if that's 5 and that's 17, this will be longer than 17. I'm going to call it, you know what? I'm going to measure instead because I really want to make the height the unknown. And I'll call it h. Okay, so is that 17? Did it make sense to call that 17? What if I do it with inches? It's too long to be 17. I'm going to say that's 23. Now we're in inches. Therefore, I have to switch this to inches, and it is now going to be closer to 7 inches. But I also want to know this. And that is going to be, I'm going to call that 19 inches. We have created another Pythagorean situation in this inside finding the perimeter of a right trapezoid, but this time we know the hypotenuse. That's what I wanted to do with this example. Write the formula. A squared plus b squared equals c squared. Our h is both here and there. Our hypotenuse is the 19. Oh, I have to do a little, I added an extra step. To figure out how long this is, I'm going to say 23 minus, no, that's not figuring out how long that is. I already know that's 7 inches. To figure out how long this is, I'm going to say 23 minus 7 equals 16. So therefore, this is 16. This, which is either the A or the B. The height that I'm looking for is the other one. So hypotenuse is 19, that's 19 squared. One of the sides, the other sides is the 16. And we'll call A the side that we don't know. I already called it H. I'm not going to call it H in here. I'm just going to stick with my A. I'm making mistakes because I'm nearly out of time. Well, I am out of time. That's why I'm making mistakes. Okay, a squared plus 16 squared equals 19 squared. And 16 squared is, I'm going to finish this problem. 16 squared is 256. And 19 squared is 361. Algebra says 361 minus 256 minus 256 equals, that's 105. Yes, that makes sense. A squared equals 105. So A is equal to the square root of 105, which is 10.25. And it was inches. I did it. Now I can do it with the perimeter. The perimeter is going to be equal to 10.25. That's this height, also this height, but we only need this one. Plus the 23, we don't need the 16. Plus 23, plus the 19, plus the 7. Very powerful Pythagorean theorem when you're dealing with trapezoids, any type of trapezoid. So that is going to be 26, 49, 59.25 inches. And I did it. I did go over time a little bit. Okay. I don't have to make these videos exactly an hour. I just try to make them an hour. So this is Pythagoras, and we're starting to see all these ways that it can be useful. But what's important, because I did intend this to be a beginner's lesson with Pythagoras, is to remember that you have this very powerful formula which works within right triangles. Make sure it's a right triangle. Don't try to use it when it's not a right triangle, but when it's a right triangle, it is useful. If you know two of the sides, you can find the other one, and that comes in handy in so many different ways. With that, I am going to say goodbye from my cute dog who's upstairs, from my non-sports jersey t-shirt that's covered in chalk dust, and from me, and I am looking forward to seeing you next time.